All right. Thank you to the organizers for having me and to everybody in the audience for bearing with me until the very end of the day. So I'm going to actually follow up on a lot of the things that Judy was talking about. She gave an excellent introduction to this beautiful field of fractional train insulator or fractional quantum anomalous Hall physics in 2D materials. To some extent, I'll be repeating that, but hopefully I'll give a bit of a different flavor and talk about some, brand. I don't have my remote is dead. That's fine. Yeah. Okay. So I'm going to talk from a theory perspective about some of what I view as the frontier directions in this field and our attempts to make progress. I need to do. My remote does work. So this work is based on a paper that came up on arXiv last month with two extraordinarily talented people. One is my student, Yuto Nakajima, who is the rare kind of first-year student who doesn't show up in your office saying, oh, I can do DMRG. Instead, he came in and said, oh, I can do category theory, which, for giving starter projects, it's a little bit intimidating. And my postdoc, Umang Mehta. Okay. So, Judy already gave us a wonderful introduction to fractional quantum anomalous Hall physics, so I'll go pretty quickly through this. But in 2023, in the context of twisted MOT2 and subsequently rhombohedral multi-layer graphene, this amazing phenomenon of fractional quantum Hall at zero magnetic field was discovered as manifest in these two nice transport lineouts, although the data has improved since I took these screenshots. So you see that actually in both cases, the blue curve is the Hall effect and the red curve is longitudinal resistance. And you see the formation of plateau-like features near dips in the longitudinal resistivity with fractional and properly quantized Hall conductivity. And at this point, many fractions have been seen, not just in this top panel, which corresponds to twisted MOT2. There's 2/3 and 3/5 represented, but now even in that material, we've seen more. And in rhombohedral graphene, even in the initial measurement, all these amazing fractions that we're seeing. And the basic physical ingredient that one needs to realize this physics is essentially the formation of flat Chern bands and spontaneous time reversal symmetry breaking. So the reason that you can get a Hall effect in the absence of a magnetic field is coming from the fact that these systems are morally behaving like magnets and breaking time reversal through spontaneous means rather than through explicit means. Okay, and what really excited me to jump into this field is that this gives us all kinds of new opportunities beyond just what we were studying in traditional fractional quantum Hall settings to think about the interplay of fractionalization, strong correlations, and also traditional types of Landau ordered phases. Okay. So, on that front, very quickly, after these original measurements came out at fractional quantum anomalous Hall, superconductivity was discovered in the context of multi-layer graphene by Long-Ju's group, not in samples with Moiré, like where the fractional quantum anomalous Hall effect appears, but instead in the Moiré-less samples, but in a similar regime of displacement field and doping to where the fractional states occur. Okay. And this led to, inspiration for many theorists of, oh, wow, what if we could actually have a material system where superconductivity and fractional quantum Hall could be realized in the same phase diagram where you could just tune between them, okay? And really remarkably, soon after those measurements, probably it was September of 2024 or something, and then this new experiment came out in April from Ting-Shin Lee's group in different material, now twisted MOT2. So you see there's this sort of back and forth, it's really lovely between rhombohedral graphene and the TMDs, where actually, this vision of being able to tune between something which appears to be a superconductor and fractional quantum Hall physics can actually be realized. Okay, so you take, essentially the same system where FQAH was initially discovered. Okay, but now these are different samples. They're probably much cleaner, and already you see several fractions represented that were not in the plot that I showed you on the previous slide. So, here, for example, we have 2/3, we have 3/5, but we also have 4/7. And as you tune doping, say, with a gate out of the 2/3 state, a couple of interesting things happen. Okay. The first interesting thing is that you go from 2/3 actually into an integer quantum Hall state, which is reentrant. Okay, and that's, if you look at these plots in the lower right-hand corner here, that corresponds to this h over e squared quantized dip in the Hall resistivity. Okay. And that's coming out of what was looking like a 2/3 quantized dip here. And then eventually you go back and do a feature that looks like it could be 2/3 again, or could be something else. And then you dump into a regime, now this left panel, this is rho XX, of 0 longitudinal resistance, or near 0 longitudinal resistance. There are experimentalists in the room, I have to be careful about that. And 0 Hall effect. Okay, so as you're tuning doping in the system, and you're going from a regime where you see maybe more traditional fractional quantum Hall phase diagram with this untraditional reentrant integer quantum Hall state, into something that appears to be a superconductor. Okay, and this leads to a really tantalizing and amazing possibility of superconductivity born from a fractional quantum anomalous Hall normal state. Okay, well, this is, like many things connected to quantum Hall, an actually old concept, okay, that carried the name of anyon superconductivity from the late 80s and early 90s, and was originally proposed to try to tell us something new about high TC. And the basic premise of anyon superconductivity is that, okay, I take fractional quantum Hall liquid, I dope electrons into it. Those electrons are going to fractionalize into a bunch of anyons with fractions of the electric charge and fractional statistics. And those anyons, say here I've drawn a bunch with charge 2e over 3, may be able to get together and conspire to form charge 2e objects which are bosonic and could condense to form a superconductor. Okay, there's a little bit of a perversion of what happens in the kind of traditional models, and lately some of the attempts to fix issues in those models. But this is a cartoon picture, which, particularly for the purposes of this talk, you can just have in your head. Okay, and now that this idea has been resuscitated, there have been many, many papers connected to this subject coming out from theorists with all kinds of different opinions, some with direct connection to the experiment, some actually even predating the experiment by a few months, others speculating more liberally. And this talk will be in that last category of speculating more liberally. So I'm going to leave experiments now and ask some sort of more broader conceptual questions. So, in particular, one question you might want to ask, say, you meet a superconductor in the lab that you might think or hope is born from a fractional quantum Hall normal state. How would you actually be able to tell that the physics of anyons and fractionalization is playing a role in the formation of superconductivity? So in particular, the generically expected phase diagram looks something like this. You have a fractional quantum Hall plateau that lives at 0 temperature. As you dope it and heat it a little bit, you induce It's called an anyon gas. Okay, you have some anyons that are wandering around, they're itinerant, and eventually they condense into those charged 2e objects I was showing you before and form a superconductor. Okay. And in order to make sense of the physics of this phase diagram and how you might distinguish practically this phase diagram from a traditional phase diagram for superconductivity, we need to actually understand observable properties of this anyon gas normal state. Okay. And in particular, the subject of this talk is going to be the regime of very low density and very high temperature, which I term the dilute anyon gas. Okay. And in particular, say I wanted to compute transport in this regime, say with the Boltzmann equation or something, it would be nice to actually have a starting point for doing that in the form of a distribution function for anyons like Fermi-Dirac or Bose-Einstein, like we meet in our elementary stat mech courses. Okay. And for this talk, I'm going to give you just that. Not only am I going to give you just that, I'm going to give you just that for actually any kind of anyon gas, abelian or non-abelian, that you can possibly imagine. All right. So before I get there, I just want to do a very quick overview, since there are students in the room, of what I actually mean by anyons. I've been using this term kind of recklessly so far. So anyons are particles with fractional charge. Okay, they're the basic excitations of fractional quantum Hall states. And they carry also fractional statistics under exchange. Okay, so if I have a wave function of many anyons, it looks like this. So these x1 through xn are anyon coordinates. My wave function under exchange of different anyons, say a process like what I've drawn the lower left corner, will change by some matrix U. For abelian anyons, is just a phase where the phase is between 0 and 2 pi. Okay, so fermions are pi, bosons are 0. And for what we term non-abelian anyons, which were discussed a little bit in several talks that we've seen so far, this matrix U can be somewhat more complicated, and these wave functions under exchange can transform in some degenerate space. Okay. Another property of anyons, in addition to the fractional charge and exchange statistics, is a property that will actually play a starring role in this talk, called fusion. Okay, so anyons can get together, as I've drawn here, okay, and form separate additional anyons. So for abelian guys, it's a pretty simple process. You basically just stick the anyons on top of each other. Say I have a charge E over 3 and another charge E over 3, I'll get charge 2E over 3. But for non-abelian anyons, there can be different types of fusion outcomes. Okay, so it's not just the directly stacking them on top of each other. There are multiple possibilities for what can happen. Okay. So I've told you in lightning levels of detail what anyons are. Now, what do I mean by the dilute anyon gas? Okay, so say that I take a box of, say, E over 3s or E over K here, where K is any odd integer. Okay, so these would be the elementary excitations of a Laughlin state. And if I heat this box enough, and if the anyons are at low enough density, it turns out, and I'm skipping over many details here, if you're interested, you can check out the appendix of our paper, but basically in a regime where the anyons are sufficiently hot and dilute, the inter-anyon interactions become sufficiently screened, rendering the problem what we'll call morally free. Right? And just to make this quantitative, okay, we have that the dilute regime is one where the density of anyons is rho divided by the anyon density of states, which, okay, that's dynamical input, normalized by this 1 over k, which you can think of as like a coupling constant associated with the anyon exchange statistics, is much, much smaller than temperature. Okay? And if you cover up this 1 over k, this would look very familiar to you as just the usual dilute approximation that you meet in statistical mechanics courses. All right. So naturally, this expectation is not something totally new. Okay. And this problem has been studied on some level before, right? Like many things in quantum Hall. And there are two things I would call major early results. I'll go through these quickly since I don't have a huge amount of time. Okay, the first was a beautiful calculation by Arova, Schrieffer, Wilczek, and Z in the mid-80s, where essentially what they were doing was computing the ideal gas law for anyon gases by, in this dilute regime from the previous slide, assuming a particular cluster decomposition. So they basically were looking at the splitting in energy between 1 and 2 anyon states and computing the corrections to the 2 anyon energy. So you look at the 2 anyon energy minus 2 times the 1 anyon energy, and they looked at the order 1 over k corrections to that. Okay? And they got this very elegant, what's called second virial coefficient. If you don't know what that is, that's fine. But which is periodic in the anyonic statistics. Okay, so that was, this is really cool. Anytime you can see the periodicity of statistics, it's really cool. Subsequently, attempts were made to have a more expansive viewpoint of anyonic stat-mech, and particularly trying to form some relationship between exclusion statistics and exchange statistics. And this came through a concept introduced originally by Haldane and ultimately got named Haldane exclusion, where you imagine if you have a fermionic system, you have a state, you put a fermion in that state, you try and put, and that reduces your dimension of your Hilbert space by 1, and you can't put another fermion in that state. Now you can imagine trying to analytically continue that fermionic story away from 1. Okay, so every time you put a generalized statistics particle into a state, you reduce the dimension of your Hilbert space by a fraction, and you can ask what type of stat-mech problems you get from that. And in particular, this led to the original proposals for distribution functions for anyon gases, which came from Yongxi Wu and others. But actually, these constructions have several issues. In particular, if you try and write down a partition function that corresponds to these distribution functions, you'll get terms with negative weights. Okay, these were to some extent resolved, but not in a way that allowed you to preserve the usefulness of the distribution function. Yeah.
Level of like SU2 or level K or something?
Yeah. I mean, it doesn't have to be SU2. So all of this stuff, by the way, here you probably should just think of this as Laughlin. So it would be like U1 level K. Yeah. No, there was never any work from this angle on non-abelian states. Yeah, and so actually it turns out that and we were surprised we'd already started working on this problem before we were aware of this literature. There's a huge number of papers written on this topic, actually in the integrability world, and in particular in the context of 1D models. But really the progress of extending this and adapting this to the 2D anyon gas problem has been fairly limited. Good. So we're going to take a somewhat different approach. Mic echoing. And instead try and zoom out a little bit. The old approaches emphasize the splitting in energies that you get as you put individual anyons into into states with finite numbers of anyons in them. Instead, we want to think in the thermodynamic limit, and we want to think in terms of, okay, what is the minimal and universal topological data that you need to really discuss this stat-mech problem of dilute anyons, okay? And one of the basic assumptions that you need actually is something that's very natural, okay? Your anyons need to come from microscopic electrons or bosons. And it turns out that that constraint is going to have interesting consequences, okay? And okay, on a more concrete level, our approach is leveraging something called the unitary modular tensor category and its affiliated constraints on anyon fusion. Okay. By the way, this is the only time that UMTC will appear actually in this talk. If you're interested in that angle, you can look at the paper or talk to my student. And in particular, in this talk, I'm also going to neglect braiding corrections to multi-particle energies. I think that this is justified, and we can chat more for details on that later. But in particular, the reason I think that that's not necessarily going to be super important is that braiding corrections will actually be subleading compared to consequences of fusion constraints. And we'll find actually that there are natural anyonic analogs of the exclusion principle that arise directly from this general structure. Okay. So, all right, now let's actually dive into what we actually did. So I mentioned the key ingredient is just going to be this simple notion that, if I dope electrons into my system, those electrons should split into anyons. In other words, physical states of doped fractional quantum Hall systems should accommodate fusion back into electrons. Okay, in other words, I've depicted two states here. On the left is a physical state. Okay, you have what's called a local particle in more formal parlance, which could be an electron or a boson. But let's just stick with electrons for now. And you put this guy into your fractional quantum Hall state, it splits into anyons, and all these anyons accommodate fusion back into the local particle. Okay, don't worry about this notation below. I'll explain it in a minute. Now, you can also have states like this, but actually you can't have them. Okay, so you could write this state where you have a local particle that's able to split into A, B, and C. But if D doesn't accommodate fusion back into an electron, you're kind of hosed. Okay, this is a state that's not allowed. It's not gauge invariant. One way of phrasing this in the language of statistical mechanics too is that really we're going to be interested in statistical ensembles where you can imagine that your bulk system is hooked up to leads of electrons, and you want ultimately your system to thermalize with those leads. Okay, so you should be able to exchange particles that are electrons, but not necessarily just have anyon. You can't have an anyon go from the bulk of your sample into the lead. Okay. Yeah.
Does that mean you have to have a mention 1/2 fermion in the primary spectrum, or it's not as strict as that?
It's not quite as strict as that. So for fermionic topological orders, the answer is yes, but we can do this for bosons.
I see. Okay.
Everything in this talk is easier for bosons. That we had to actually do some new formal math to do the fermionic case properly. All right. So now let's actually talk about real consequences of this constraint. So we can write the partition function for a system like this in this kind of funny way. So you see this math cal n that's coming from the previous slide, and you have these Boltzmann weights. All right, so these little n's, these are the anyon occupations. These epsilons are the anyon dispersions. Okay, that's going to be dynamical input that I put in. Right? In principle, I can derive this from a Chern-Simons matter quantum field theory, but for the purposes of this talk, we don't need that. And these math cal n's are what we call fusion singlet coefficients. So these are essentially combinatoric factors that count the number of ways that a particular configuration of anyons can fuse back into electrons. And they also involve the braiding phases. So, in particular, you can morally think about the existence of these ends and the fact that these ends vanish for unphysical states is like an anyonic generalization of the exclusion principle. All right. Now, I can write this down formally, but there's an issue, which is that for finite numbers of particles, this math cal n is really hard to calculate. Okay, it's a very complicated object in terms of what are called mock S matrices, if you are familiar with the UMTC language. And it turns out, though, that there's a neat trick that you can pull here that works surprisingly generally, right? So it turns out that in the thermodynamic limit, this n factorizes in a really nice way, where it actually just turns into the product of the quantum dimensions. So we met the quantum dimensions in several earlier talks. Okay, you can think about this as the internal degeneracies of anyons. Okay. And these n's become the product of these quantum dimensions for each of the anyons in my configuration. Okay. So, and also I should emphasize for abelian anyons, these quantum dimensions are 1. Okay, so this just tells you that the partition function would factorize into little partition functions for each individual state, just like what you would have for a non-interacting Fermi or Bose gas.
So we're now into
5 minutes. Okay, cool. I can wrap up fairly quick. So, turns out that this formula was demonstrated in ancient times by Pasquier and Verlinde. It's sometimes called the Verlinde formula, but this is the sense in which it's easier for bosons. My student and postdoc managed to figure out how to do this for fermions. If you're interested, you can see the appendix for our paper. All right, so I told you that now our partition function can factorize like in a traditional Bose or Fermi gas into partition functions for each state, but weighted now by these quantum dimensions, right? But now there's an additional issue, okay? I haven't actually put in any constraints as far as how I'm summing over occupations that are connected to the microscopic particles in my system. In other words, I haven't actually used directly the information that my microscopic particles are bosons or fermions, okay? So in order to determine how many terms I need to sum in these little partition functions for each state, I need that piece of information, so that's the Hilbert space, in addition to some dynamical information having to do with which anyon has the smallest gap in my system. Okay. So we can codify these assumptions, I'll skip this slide, into something called, that we termed the occupation sequence. So basically you take an anyon, which you say, okay, this is my lightest anyon, it has the smallest gap. When I dope my system, my electrons split into these anyons. And I just start paying these anyons into states where the outcomes are determined by the different fusion channels in my system. So I also need to make some assumptions about which fusion channels are preferred energetically, but that's more detailed than is needed in the talk. And where the Hilbert space information comes in is that if you start paying the lightest anyon in, and the local particle you reach is a boson, you keep going on forever, okay? So that's actually how you would get an anyon superfluid. And if instead you were to reach a fermion, you stop, okay, because of Pauli exclusion. So this information can be plugged in and actually leads to a computation of the distribution function for a generic anyon gas, which we can write here in all of its glory. So this y is the Boltzmann factor. You see there are these quantum dimensions that are my weights. And these L's here, which tell me the length of these sums, in turn tell me something about the number of anyons that I can pay into a state before reaching a microscopic electron or a boson or a Cooper pair, or whatever is the local particle in question. Okay. Good. So we have a general pipeline for doing this for any topological order, but I'll go through that very quickly. I just want to show the actual results. So we can do this for abelian anyon gases as well as non-abelian. Here's the case of fermionic Laughlin state, where the lightest anyon is the elementary one. Okay, so charge E over K. In this situation, how I do my occupation sequence is I pay one anyon, then an E over K anyon, 2 E over K, et cetera, K times. Eventually, I reach an electron, and then I stop. And that leads to a distribution function, which looks like a Bose-Einstein distribution, but with a Fermi-esque correction, like what I've drawn here. Okay? And you can see that there's a distorted analog of the Fermi-Dirac distribution in this plot here. So the blue curve is the Fermi-Dirac, and the Laughlin analogs are the dashed and orange solid lines. Okay, and actually, this very closely resembles exact large N 't Hooft limit calculations in Chern-Simons matter theory. And I'm being pulled off stage, so I will, no, it's fine. Everybody wants to go home. Yeah, so I'll just show that for the case where you fuse to bosons, say that I had 2e/3 being lightest, you just get actually regular Bose-Einstein. For non-abelian states, you get that distorted in an interesting way. And with that, I will conclude and say that there are many important things that need to be done in this field. This is, of course, a very short, although the paper is not short, first step. And yeah, I hope that more people get into this field.
Two quick questions.
You mentioned there is a correction from the grading.
Mhm.
What is this? Is there a small parameter that controls the error?
It would be for abelian anyon gases, it would be 1/k. But I think actually at sufficiently high temperatures, these things are quite small. The most controlled statement I can make is that take the HOQE limit. So you do SUN level K with large N and large K, with N over K fixed, then actually your anyon gases dilute for all values of density.
This is a pretty cool talk. Could you apply this to non-abelian anyons and say quantum double model? In that case, like, is it well defined whether the underlying piece of food like bosons or fermions?
I mean, there should still be
Yeah, I mean, so like last H, we were not doing last H, we were just.
I think as long as you have like this way, so if you put in there, you should be able to form. And as long as you taught that. And actually, that's the point that I would make is that you can stop at any local point. Doesn't matter.